Okay, so hello everybody. First of all, I'd like to thank the organisers for the invitation. It's been a fantastic trip and experience so far. I've got to experience why my fellow countrymen have emigrated here, and it didn't involve a lot of sleep, but hopefully I'll catch up over the next few nights. But okay, I'm from, well, I represent the Catholic University of Leuven. Our lab is, as Don said, M3 Biores, and that stands for Measure, Model, Manage Biological Responses. And the core of the group, this is a picture of all the people in the group, the core idea is that we treat every individual, be it an animal, be it a human, even be it an insect, as an individual serving as their own reference, and we look for deviations from the normal. In other words, we look for abnormal behavior, but we do that in a real-time, automatic way. So we use the latest sensor technology to do it. And this is the group. Half of the group actually work in the area of human health engineering, and the other half work alongside myself and others in the area of precision livestock farming. So I'll talk a little bit about the reasons and the background when it comes to why we're doing this thing. We see a lot of challenges in livestock production. Most of these things I'll talk about now are focused on Europe, but you can see the similarities in the Australian system. So we know that over 60 billion animals are slaughtered every year, and that's to increase by 40% over the next 30 years. The big challenge is that we're not reaching our current, the potential of the genetics on the farm. So we need to think about how to do that in the future. Health is a big issue. Health in Europe, very recently they brought all the many regulations on health together into one law called the Animal Health Law. It fused it with animal welfare concepts, so they're integrating animal welfare and animal health and thinking about how we need to link that with human health, so antimicrobial resistance being a very important point there. So there's a lot of movement in Europe on that aspect. Animal welfare, I know there's been some talk over the conference that animal welfare standards in Europe are not that high, but in fact there's a lot of work being done in Europe particularly since 2009, to bring good protocols together so that farmers can do the assessment or have trained experts to do it for them. Okay, it's not there for every single species, but for sure it's a point that needs to be addressed in the current production systems. Environmental issues is another big challenge, as here in the Australia, I'm sure. Animal buildings have a big impact on the environment. Where we're based in Flanders in the north of Europe, there's such a density of animals per square kilometre that is really becoming a big problem. So that's another significant challenge. Another important challenge is the social importance. We see in Europe a lot that farmers, because they're being squeezed by local regulations or directives, that they're not really so proud of their systems, and that's not what we're happy about. We want to change that for them, at least help them, and that's part of our thinking. And finally, economic importance. So we also heard in the conference that Europe has taken a market of Australia, and maybe the reason was because there's low welfare standards for that particular species, but that's not what we want. As a group, we want to operate and compete at the same level. So we want to bring the technology, bring the ability for farmers to operate and compete against those high welfare standards. Okay, so I'll talk a little bit about the real challenge in terms of animal monitoring. So in the past, it was quite easy, well, because there was a limited number of animals on a farm, it was quite easy for a farmer himself to walk through the herd and to understand which animal was feeling a bit upset, which animal was ill, etc. But nowadays it's becoming more of a challenge, because the animal numbers on the farms themselves are increasing, and if anything, the number of farms are either staying the same or are starting to decline, as there is a greater need for specialization. And what does this result in? Well, if there's a high number of animals per farm, obviously the farmer doesn't have the same amount of time to dedicate to those animals. And with genetic progress and the density of animals together, there's going to be a knock-on effect on animal health and welfare. So it's inevitable that this is going to happen. Okay, so there's 3 approaches in Europe currently that focus on measuring animal welfare and really trying to monitor that in a good way. The first approach is called what we call the iceberg indicator approach. Basically, it's when the animal goes to a slaughterhouse, the carcass is checked. In the case of broilers, the pads are checked for lesions, and then it's scored whether it's good welfare has been grown in good welfare conditions or not. Okay, so but that's a quite limited approach because the farmer can't act on it. The second approach is the welfare quality approach, and this came out around 2009, and I'm sure people have heard of it here. It was a huge project with many different scientists, perhaps some from Australia. They defined protocols that now they're starting to implement. Member states within Europe have digested these, pulled them together into their own local protocols for welfare assessment. Primarily because they want to operate at high welfare standards, because the consumer is starting to expect this a lot more. So this is something, but it's a challenging thing. Yeah, this welfare quality is a process where a trained assessor needs to go to a farm, carry out the assessment, and be sure that the score he's given is representative of the farm. There's a number of problems with that. First of all, the assessor needs to be trained. He or she needs to get a suitable sample size to make sure what score they give is representative. And in the end, it's a subjective process, yeah? Because the trainer is there, well, the assessor is there, he's looking at the animals, perhaps the animals are responding to his or her presence. So we think the next step in all of this is really to move towards the automation, to look at the automatic monitoring of the animals. Okay, so these are the 3 methods along the timeline. We have the slaughterhouse, where you implement the iceberg indicator approach. Then on farm, you can, again, only once per year, or perhaps if you're lucky, twice a year if you can afford an assessor. You can do a welfare quality approach for welfare assessment. But if you use automated technology, what we call precision livestock farming technology, then it's possible to do it 24/7, 7 days a week, every single day during the year. And there is no subjectivity. So that's our purpose, to bring this technology to the farmer. So the precision livestock farming area, what is it? Precision livestock farming itself, it doesn't have to be done with sensors or technologies. It's a set of methodologies, practices that farmers can implement to make sure their process is efficient. However, we're in a day now where we have many different types of sensors, we have different types of devices. It's very useful for them to use those devices to optimize their approaches. Yeah? And we see that with the plethora of data, the amount of animals that they need now to look towards these technologies. So the technologies for welfare, for production, for health, and a lot of these I'll talk about in a few minutes, and for environmental monitoring. And together, we consider precision livestock farming to be a set of tools or tool set that enables sustainable livestock production. Okay, so the area of precision livestock farming has started many years ago, and it's progressed from the EU, although there has been some Australian scientists, and I know recently there was a conference in New Zealand with, again, a lot of Australian scientists on the area of precision livestock farming. So there's been plenty of conferences, a number of projects. We recently just finished the largest EU project on precision livestock farming, where we were coordinating it, where we had about 20 different partners, 20 different farmers, and we implemented the technology, took it out from the lab, brought it into commercial practice, and see how did this stuff create value for the farmer. Okay, so let's talk a little bit about what Precision Livestock Farmer, or PLF, is we use a scheme, just a diagram that represents the approach we use. Yeah? So if we consider everything around the animal to be its microenvironment, these are influencing variables on the animal. It could be temperature, humidity, feed, water, etc. By looking at these as inputs and then looking at the response of the animal to these inputs as the bioresponse, we can start to measure the response of the animal in real time, provided we have the sensor technology to do it. And often cases it's there. One very popular example is image camera systems. The other one is sound systems. I'll talk about two applications of those in a few minutes. So we measure those responses. At the end, we measure the inputs going in, and then we define some algorithms. So that's where the computing comes in to try to make that correlation, that link between the inputs and outputs. And that allows us then to set thresholds, to monitor it over in real time, to continuously adapt to the growth of the animal or their evolving behavior based on their age, and to determine then if they're deviating from what we believe is normal or not. So it allows us to do some managing and monitoring. So what are the examples? Well, one example that is very useful for us, because it ended up in a spin-off company. They now have a technology on the market. They're working with one of the world leaders in animal health. This is sound monitoring for infection, sound monitoring for cough analysis in a pig house. So basically, it's a microphone that's installed in a pig house, and it detects the number of coughs over time. And this was done in collaboration with different partners. Our group designed the algorithms, so we do the more algorithmic work in this type of development. And the idea was, in this system, to try and automatically detect the coughs. Of course, the cough itself will have a different characteristic in terms of its sound to the other different noises that happen in the room. So we need to separate all of those. You will have doors banging, people shouting, chains banging, machinery turning on, ventilation system. You wouldn't believe the amount of noise you have in a pig house, and you need to single out one cough from that, and it's quite a difficult process. It took many years to develop it properly. And this here is the system. So that noise is a pig. So that's what we're looking for. But of course, here we have something in the lab, so it's very nice. But in reality, you don't get that kind of clarity at all. Then this is an example now of where this system was implemented. It was a blind study where the farmer wasn't told about the output of the pig cough monitor. And it's labeled here based on what the farmer did. So he just responded to the vet's reactions to the health status of the pigs. And from this system, the pigs entered the building. Immediately they were coughing. Perhaps it was because they changed the environment. Then after a few days, the pigs, the vet noticed they needed to be treated. The farmer treated them, but obviously they didn't respond to the treatment. So from 4th of November onwards, you see the infection is progressing, but obviously because the farmer is treated, he thinks the problem is solved, but it's not. And this is some insight that the system can give us, and I think this is a fantastic thing about it. And of course, again, we see pigs are treated perhaps a bit too late after that point, and then they become ill again and never treated after that. So it's a very interesting approach. Farmers don't look specifically for pigs coughing. They think they understand the level of health in a building or on the farm, but sometimes it's a real challenge. They have so many different things to do. So we see the main future progressing towards the use of antibiotics, reducing it, targeting diagnosis, etc., to enable the vet and enable the farmer to remove the infection as quickly as possible and minimize the use of antibiotics. So that's where that technology is going. The next one, again, is focused on health, but this time with respect to the behavior around the drinker. So, of course, the animal will change its behavior if it's sick, so it might drink less. If it's a bit sick, it'll eat less as well, and there's a ratio between eating and drinking. And here we wanted to use a camera system to detect the frequency of visits and duration of visits to the drinker. And here we collected some images. We did some modeling on those images to relate them to the water meter, and then we just compared to see, well, whether we could predict well what the water meter measured just using the camera. That's what we did. Okay, so in this slide here, it shows what the algorithm does. So the pig goes over to the drinker, and once he's in the vicinity of the drinker, you can see there that the line goes up above the threshold. So the algorithm recognizes the pig is at the drinker, and now just the pig is starting to move away. The algorithm says the pig is moving away. This is the duration of the visit. So it's in principle quite a simple idea. And of course, it does sometimes give very nice results. Other times, when pigs foul with the water or play with it, it isn't so well correlated. But it gives a good indicator on their water use and an indicator for health. Another application, this time in terms of welfare, is the use of cameras in a broiler house. So we work with a company, have done so for many years, who have developed a technology called iNamic. It's basically a number of cameras that look at the flock of birds underneath, so they're installed on the ceiling. And 3 or 4 different cameras would cover a full broiler house. And the farmer then would just view the indicators that come off the camera. So 2 indicators come off the camera. One is the activity of the birds, how much they're moving, and the other one is the distribution of the birds, how uniform they're spread over the building. And this is just the monitoring software that's used to do the image processing. This is how it's laid out. The green thing on the right-hand side is how the birds would look in the algorithm, so it recognizes that these are the birds and not the floor. That's all it does here. So by taking that data then, it's possible to look at the distribution. And the distribution, like I said, is the spread of the animals across the floor. And so what we try to do is model that spread over time. And basically, it's quite, in the end, very simple as well. We look at the individual light periods, and we get an estimation then on what the likely distribution would be for the next light period. And if it deviates by 20% more than what we estimate, then we raise the alarm and send that to the farmer. So if there's over a 25% deviation, an alarm is sent. This case, on the left-hand side shows that there's no deviation, it's quite uniform, whereas on the right-hand side, there's a blocked feeder line, there's a deviation beyond 25% of the value. Okay, so that's the idea. In essence, it's quite simple. The key thing is to work with the farmers. These guys are they understand the process, and that's why we need to work very tightly with them to make sure we set our thresholds right and allow these maybe to vary if needed over the cycle. And another thing, when we validated this, 95% of the time, each alarm was related to some problem in the house, related to welfare. So whether it was litter condition, feeder line block, drinker line block, etc., we were able to detect it with that algorithm. The next application is in the area, again, of welfare, but this time with pigs. Pigs, as we all know, like to fight when they get together, especially when they're mixed or something's changed in their location. It's okay to get the ranking in a pen, but after that it starts to take the energy and deviate it towards just coping with these interactions rather than actually putting down some muscle. And we took it upon ourselves a number of years ago to try and come up with an approach that was able to detect when these interactions became too severe and then act on that. And the action that we decided to take was dispense a sweet which the animals recognize is being dispensed, and that will stop the fight. So early on, when they were being reared in the nursery, they were conditioned to recognize a sound signal and associate that with a sweet. Okay, the M&M, like the pigs like, we learned pigs like M&Ms. And so here is the case anyway where we have the algorithm working. Down the bottom you see the pigs are fighting now. These two images on the bottom show that this is the algorithm. It uses up and down movement as well as left and right movement. But just in a couple of seconds you'll see the pigs stop now. So the sound was raised. So everybody is, all those pigs have stopped. They're waiting around for the sweet. It probably fell through the slats. But it doesn't stop there. Of course, they're getting a bit bored and off it goes again. So it's not the solution. It might be, if we tweak it a little bit more, we need to do more work on that. There's a lot more questions to ask in this case, but we're finding some very interesting results with this. Okay, so if I look at another aspect, which is continuous automated monitoring of feed intake, this time for, let's say, for monitoring and making sure there's no waste in the feed coming into the building. We have developed a system to try and monitor the intake of broilers, and that's a big challenge. Feed intake for broilers, feed intake for any animal is a real challenge. It's completely different to what you give them from what they take in. So if we could really monitor that well, we'd get a lot further than we are today. So what we did anyway in this case was we said, with the feeder tray, it was only a tray because it was done at a lab scale, we attached a contact microphone, and each time the bird pecked for the feed, we registered that pecked and linked it with the amount of feed the bird took up. So therefore, the end objective was to try and link the pecking noises with the quantity of feed that was taken in. And here is, so you can kind of hear the pecking here. But you can't hear it so well because in the lab it's a noisy environment. So there was some ventilation heater systems, and those top two graphs show that there is noise in that signal. There's only a few, but you can see the pecks, these clear, distinct moments where there's pecking. And down below, we did some filtering to remove all that noise, and I think you can hear it. Yeah, you can hear it. It's definitely more clear than what we had before. So what we did was, with the pecking, we were able to link the number of pecks with the amount of feed taken in, and it proved to be very linear, really nice correlation on the left-hand side. And then we implemented that in order to validate, and of course it reasonably well followed the same trend as what was measured with just the weighing scales. But of course, there's going to be some dropping of the feed from the bird's beak. It doesn't make it in the whole way, but it's a good start anyway. It's a solution. Perhaps we can look at some way of refining it into the future, perhaps with image or something. The next one on the productivity is looking at animals, weighing animals, pigs in a pen. So I already showed you the application of the camera to look at drinking behavior. That same camera now can be used to estimate the evolution of weight in the pen. Very high commercial value for the farmer. You can determine which pigs can go to the slaughterhouse in the house. So it's a very useful tool. The reason this is a lot different to other systems is that it's not constrained by having to be in one particular area, like over a feeding system or something. We just put a single camera over the full pen and we weigh them then. We get a group average, and that's useful for the farmer. Okay, so I'll do one more case where we see the evolution of all this technology going, because we had a lot of talk here about welfare. Of course, you have very high welfare standards. We have high welfare standards, but perhaps for the market that is competing with you, it's not operational. But we feel that welfare can be monitored in very new ways. In the past, we used these other approaches of sound and image. Now we're going to look at other approaches here. So this case is a case which has come out of a spin-off of the group, our research group. They look at designing algorithms to monitor the stress levels of people. So they captured 3 variables. One variable is heart rate, another variable is temperature just in the vicinity of the skin, and the next variable is movement. And they integrate those variables to look at the stress that an individual is feeling at any one time. So in other words, if you're sitting down, if your heart rate is high, you're more than likely stressed, but if you're walking around and your heart rate is high, your heart rate is linked with your physical activity. So it's really trying to separate those inputs into your heart rate and define whether you're actually stressed or not in particular situations. So, and the idea around it is that, yeah, for every individual, there is an optimal region where we need to be stressed. We need to be stressed enough in order to be motivated to do something. But the problem is if we get too stressed, then we're likely to make mistakes, forget things, etc. If we're not stressed enough, well, then we're likely to drop the situation or become unmotivated and forget about it or do it wrong because we're not motivated. This idea has found applications in stress at work of typical people in typical workday environments, but also in kind of very difficult environments in sports. And I'll show you a case where it's been applied for Formula 1 drivers. So the next video shows that. And here I'd like you just to look at the graph on the top of the video. There is a green band on that graph, and that green band is the optimum zone of stress for that individual. The individual driver is wearing the device to capture heart rate, temperature, and movement. So we can monitor this stress level in real time and see does it influence how the driver behaves, his driving behavior. And you'll see it does. So at this stage, he's trying to pass out the guy in front of him. You can see he's getting stressed, yeah? That the stress is going outside the comfort zone. But he passed him, so it's dropping. But now something happens. He's starting to get stressed again. And you wonder why. He's trying to make time on his lap. So he's trying to push it on this lap, and he's becoming more stressed. And now he's going to make a mistake. You see, he made the mistake because he was overstressed in this situation. We're able to monitor that in real time with the system. And the idea is that this then can be used by the team to give advice, to tell him act in a particular way around the track. We believe, well, we have proven that it can also be brought to animals. This approach has already in the past been published. We have already implemented heart rate monitoring and movement sensors on the animal, linked the movement to the heart rate, and then found that any deviation of heart rate above that normal value is due to stress. So in this case, we can show a case where a horse is being lunged. The horse is wearing the activity sensor and the heart rate sensor. We build the model, and then we give a stressor to the horse. So we, in this case, bring out an umbrella and flash it, and the horse becomes stressed. And what happens then, the connection between moving and heart rate doesn't exist anymore. Yeah? And that's when you get this stressful alert. Okay, it should work. Sorry about that, it doesn't work. But it worked earlier, but yeah, okay. So the horse is being lunged. Now somebody's coming out with an umbrella. And that's just the very middle point of that graph where the heart rate gets higher and it deviates from what we model. So that's the idea there. But in this particular case, we had a very interesting result. Right at before the umbrella was revealed to the horse, a farmer turned on the machine next door. And this wasn't something that was picked up straight away. When the student went through the data, they didn't have the sound on the computer, so nobody knew why this stress thing happened at the beginning. But it's very clear in the video when you have the sound in. It's that moment that's flashing there. You hear? The tractor was turned on. So there you got an elevation in heart rate, which wasn't well connected with the activity, because the horse continued to move around, but he was still stressed because that situation of the stressor. So this is where we see the future with this. Okay, I'll just finish up on this concept that a key aspect of all this is having the right business models. And we heard a lot during the conference about trust and distribution of trust and having contracts within a supply chain. But I think this technology has a very fundamental part to play there, because with solutions like this, we can start to move data freely across the supply chain, allow the supply chain to optimize itself. There's movements in Europe to try and do this. There's a very big project happening at the moment called Internet of Farming and Food. And this is trying to realize these ideas. But here we came up with some concept for the business model that might work. So we have, in the middle of this business model, a provider of this technology and these data services. This provider can link with vets, breeders, other stakeholders who are interested, for instance, researchers if they need to use the data. It also links with the supply chain, the farmer, the feed, all the way slaughter, exporters, for yourselves. Everybody who's involved in this can be connected. And then link this with the consumer. The idea being here that if everybody is treated in a fair way, well then the technology can be affordable to the farmer. Because at the moment, this technology, they see it as a block, the pricing of this technology. So we're trying to come up with different concepts to enable this cost sharing, this distribution of cost across the chain. Of course, everybody needs to find their own place, their weighting in terms of pricing in this kind of model. Okay, so I'll finish up on this. Here I just give some ideas on where we see it in the future. As part of the livestock sector. So of course, precision livestock farming, as I introduced, can give very detailed monitoring of the animal, and in real time, it can then allow the animal to take part in the management of the farm. They're in fact driving the farmer to treat them in the proper way. And it enables and also quantifies sustainable agriculture, because we're getting numbers from these things. We're not getting people drawing, assessing situations. We're actually getting real numbers. And something that's of interest, I think, to you and to us, is that it's a way to implement welfare standards at an agreed level across countries. I think we should collaborate in the development of this, because then we'll reach something at a kind of a shared level where we have some mutual understanding where things need to go. I think that's what should happen. And a good thing about that is Australia are participating in a lot of the European funded calls. So it's one way of getting this exchange and transfer of knowledge. And of course, it's a way, because it's technology, we can start making the data more transparent. What the farmer is doing, his best practices can become evident. The consumer has the opportunity to pay more money for those things that are more costly. The opportunity, of course, is one thing. Whether they do it is another thing. We need to change behavior too. This is part of the overall solution, but not the final thing. Okay, so thank you very much for your attention. And if you have any questions, I don't know if we have time, but I'm happy to answer.